Good morning, my name is Marinélia Capela. The title of my presentation is Biomass as Fuel, its influence on the characteristics of the produced ashes. In the pulp and paper plant under study, large quantities of fly and bottom ashes are produced from biomass combustion in bubbling fluidized bed boilers for heat and power production. These ashes must be considered as an integrated part of the biomass to energy practice for the sustainability of the whole process. The attempts to valorize these wastes are challenging because their temporal variability in terms of physical and chemical properties. One of the main factors affecting the properties of the produced ashes is the fluctuation of daily biomass blends used as fuel. So, the aim of this work is relate the biomass blends used as fuel with the ashes characteristics to establish better management practice. To access the influence of each biomass type in the produced ash fluxes, they were individual subject to a controlled combustion process in an oven at a maximum temperature of 825 degrees Celsius, which is the typical operating temperature of the bubbling fluidized bed boilers at the pulp and paper plant. The biomass typologies found in the feedstock are mainly eucalyptus bark, eucalyptus treetops, and pine treetops. Other species, such as silver wattle, Sydney golden wattle, white poplar, and grey willow are also present, but in smaller amounts. The obtained ashes were characterized in terms of chemical composition by X-ray fluorescence. The loss on ignition at 1000 degrees Celsius was also determined. Particle size distribution by laser diffraction on a Coulter particle size analyzer. Specific surface area by physical adsorption of nitrogen gas using the Brennauer-Hammett and Teller method. Microstructure by scanning electron microscopy coupled with X-ray energy dispersive spectroscopy. And mineralogical composition was assessed by X-ray diffraction, and a semi-quantitative phase analysis was also performed. The major elements present in the chemical composition of the ashes, determined by X-ray fluorescence, are shown in Table 1. From this result, the potential of each biomass feedstock as a source of inorganic elements can be evaluated. For all the tested biomass types, the obtained ashes are mainly composed of calcium oxide. Potassium oxide is the second most abundant component, except in eucalyptus bark and eucalyptus treetop samples, for which is magnesium oxide. The ashes obtained from the acacia species, silver wattle and golden wattle, have the highest chlorine content. Samples silver wattle and pine treetops present the highest values for sulfur trioxide. Loss on ignition values are quite different, ranging from 3.89 weight% for golden wattle to 10.4 weight% for eucalyptus treetops. Here, in Table 2, are presented the minor elements present in the chemical composition of the ashes. Chemical elements such as scandium, vanadium, chromium, nickel, molybdenum, cerium, neodymium, lead, thorium, and uranium are present in all the ash samples, and it was observed a large variability in their concentration. Figure 1 presents the SIM micrographs and the IDS maps of the biomass ash samples. The ash particles have a large size diversity, an irregular shape, and not smooth surfaces. The IDS maps show the distribution of the chemical elements present. As expected, the most intense pattern, in yellow, corresponds to calcium. In the case of poplar, The potassium pattern in blue is also quite intense, reflecting the higher content of potassium in this sample, in accordance with the X-ray fluorescence results. Here, in Figure 2, we can see the particle diameter distribution determined by Coulter for the various ash samples. All samples exhibit a largical particle size distribution, ranging from submicrometric size to dozens of microns. Golden wattle is the sample containing the coarsest particles, approximately 75 micrometers. The specific surface area, the mean particle diameter, and the percentage by volume of the different particle size fractions are shown in Table 3. The sample that has the highest mean particle diameter is golden wattle, 15.62 micrometers. On the contrary, the lowest is observed for pine treetops, 4.64 micrometers. The higher value obtained for the specific surface area was observed for pine treetops, 5.99, and the lowest for golden wattle, 2.22. Results of the semi-quantitative mineralogical composition of the ashes, evaluated by X-ray diffraction, are presented in Table 4. All samples present two crystalline phases, lime and periclase. For all the samples, except for silver wattle and Sydney golden wattle, hydrated lime was detected in addition to lime. All samples, except for eucalyptus treetops and eucalyptus bark, present arcanite in their constitution. From the results of the present study, it can be concluded that the physical and chemical properties of the ashes obtained after combustion at 825 degrees Celsius are greatly influenced by the type of biomass used. The biomass samples exhibit quite different loss on ignition values. The main component of all the ashes is calcium oxide. The other main constituents are potassium oxide, magnesium oxide, silicon oxide, phosphorus pentoxide, sulfur trioxide, sodium oxide, and aluminium oxide. The ashes obtained from acacia species are the ones that contain the highest chlorine content. Samples silver wattle and pine treetops present the highest values for sulfur trioxide. The ash particles have an irregular shape, a rock surface, and a large size diversity. All the ashes have lime and periclase. Arcanite is present in all the ashes except in eucalyptus treetops and eucalyptus bark. Calcium hydroxide is present, resulting probably from lime hydration. The biomass type has a huge influence on the ashes characteristics. It's mandatory to prepare blends, biomass or ashes, to use this waste as secondary raw material. Thank you for your attention.
Hello, my name is Ricardo Carvalho and I'm a postdoctoral researcher at the University of Aveiro in Portugal, and this project was developed at the Center of Environment and Marine Studies. Um, this work has been developed with Gloria Ramis and Ana Dias, my supervisor at the University of Aveiro, and our colleagues and partners Cristina Marques, Ana Carta, Luís Machado, from the Forest and Paper Research Institute in Portugal. The project and the work has been developed under the framework of the Impactus project, Innovative Products and Technologies from Eucalyptus, a project that has been led by the Raiz and the Navigator Company. This work presented today is an environmental sustainability assessment of tissue products, comparing an integrated production with an unintegrated production, and has been developed in the framework of our group life cycle-based sustainability assessment tools. Tissue is an important product and has been increasing in consumption. According to the World Tissue magazine, the global tissue consumption is expected to continue growing until 2027 at a growth rate of 3.3%. So this motivated our work and the demand for the development of local sustainable industries for producing low-density tissue papers. Our goal in this project was to compare an unintegrated mill with an integrated mill, applying a life cycle sustainability performance assessment focused on the environmental analysis. So to be more specific, we evaluated two types of tissue products produced from kraft pulp, one domestic and another for industrial use. And our objective was to determine the benefits associated with an integrated production with pulp and bio-based energy. When I say integrated production with pulp, is an integrated production via a pipeline in relation to an unintegrated system where there is no integration of the material, neither the integration of energy. And we also aimed to identify environmental hotspots along the value chain of the tissue products. So just to give you an overview about the life cycle assessment framework under the ISO 14040 and 14044. First, our goal was to determine the system boundaries, so the goal and scope definition. We analyzed 4 scenarios. 2 scenarios for the domestic project and 2 scenarios for the industrial product. And for both products, we analyzed the system as non-integrated or without any material and energy integration, and the system with integration of eucalyptus pulp and bioenergy from the pulp mill to substitute natural gas in the boilers of the tissue mill. And we have done the same for the industrial and domestic products. The study was conducted from cradle to distribution, including the forest, pulp mill, tissue mill, and distribution stages. Our functional unit means that all the environmental impacts are calculated, estimated in function of the functional unit. Our functional unit is 1 ton of tissue paper, and we analyze the impacts for the domestic and the industrial product. Basically, and looking at the system boundaries, our tissue products are produced from with a fraction of eucalyptus that is mainly produced in Portugal, and softwood that is produced overseas in Central and Northern Europe. The eucalyptus produced in Portugal is transported to the pulp mills in Portugal and then transported again to the tissue mill. And the softwood produced overseas is also transported to pulp mills overseas and then finally transported to the tissue mill in Portugal, which is then connected to converting lines that produce the 2 products, and then they are distributed in the market. In our study, we considered the Iberian market. Then we tested the integration of pulp and energy from the eucalyptus pulp mill to the tissue mill. The next step was the inventory analysis, where we analyzed all the inputs and outputs of our process, of all the processes in the assembly or in the life cycle value chain. So we analyzed, we collected data for the raw materials, the auxiliary materials, the water, electricity, fuels, and then the outputs, emissions to air, to water, to soil, wastewater, solid residues, and all this calculation, all this data was then converted to basis in function of the reference product. So our reference product is 1 ton of the output in the process. Important is to point out that the data was collected from the industry, so we call it foreground data, and also we combine it for some process we haven't got the data for the industry. We combined it with background data from the globally well-known and credible database EcoInvent. Finally, we have applied a life cycle assessment method, and we used the recipe to 2016. And this impact assessment method includes different impact categories. We decided to focus our study in the global warming category, which is related to the greenhouse gas emissions, terrestrial acidification, which is related to the damage to terrestrial species due to the deposition of inorganic substances such as sulfates and nitrates, and then the eutrophication categories, one associated with damage to freshwater ecosystems and discharge of nutrients into soil or into freshwater bodies, and the marine eutrophication related to the damage to marine ecosystems due to the discharge of those nutrients into soil or into marine bodies. Finally, we analyzed the mineral resource scarcity and fossil resource scarcity categories, which are respectively related to the scarcity of certain minerals, such as aluminium, uranium, copper, and iron, or the fossil resource scarcity that is related to the scarcity of fossil resources, such as oil, natural gas, and coal. This method is based on an harmonized life cycle impact assessment method at midpoint that was developed by the National Institute for Public Health and the Environment in the Netherlands. So showing the results, in general, the tissue mill was the process stage, the life cycle stage with the highest impact, followed by the pulp mill. This is due to the high consumption of electricity, and in the case of the pulp mill, due to the consumption of chemicals. So for the global warming category, the improvement with the integration was up to 25%, so pretty significant. And the difference between the industrial and domestic product was about 8% better for the industrial product. The same trends were observed for terrestrial acidification, with improvements up to 14% with integration and 6% better for the industrial product. For the categories of freshwater eutrophication, the same trends continue to be observed, with improvements to up to 17% and up to 7% for the industrial product. But for the marine eutrophication, the situation is different, and here there is a trade-off, since the integration reduces the performance in 11%. And as we can see in the figure, the tissue mill is not anymore the process that dominates the impacts, but the forest production. So this is associated with the fact that we are transferring bioenergy to the tissue mill, and this bioenergy has emissions associated with the forest management systems. And in this case, we have an increase of about 1% For the domestic product, the product is the industrial product is 1% better, so not really significant the difference. So important is to point out that this impact of the forest system is associated with nitrogen emissions. Marine eutrophication is more associated with nitrogen emissions with nitrogen-based compounds, and the freshwater eutrophication is more associated with phosphorus-based emission compounds. So finally, we will show some results for the resource scarcity categories. For the mineral resource scarcity, it's pretty clear that the domestic product has much more impacts, up to 38% more impacts than the industrial product. And this is related to the materials used in packaging. So the differences observed from the improvement of the integration are not very significant in this case, but what is more evident is actually the difference between the two products. And for the fossil resource scarcity, we can observe the same trends as for the global warming. So I will not comment very much on this case. For the conclusions, what we can see overall is that the tissue mill is the life cycle stage with the largest environmental impact for the majority of the categories analyzed, and integration of pulp and bioenergy from the pulp mill to the tissue mill leads to a reduction of environmental impacts in general, but this is more significant and expressive for the fossil resource scarcity and global warming categories, since by using bioenergy and by using less energy when we transfer the pulp via pipeline, we don't have so much use of fossil resources and we don't have so much emission of greenhouse gases. So finally, the pulp and energy integration causes an increase in 11% in the marine eutrophication, fact that is associated with the production of biomass fuel and the allocation of impacts from the forest management stage. This biomass is produced and transported to the mill and then is combusted efficiently to produce bioenergy. So finally, I would say that further work should include a social and eco-efficiency analysis of this and all the configuration of integrated pulp and paper mills. Thanks for your attention. I would like also to thank this work to the PT 2020 that funded the Impactus project and the COMPET program 2020. And additionally, I would like to thank the Foundation of Science and Technology of Portugal and the Ministry of Science for the financial support to our center, CESAM, and our University of Aveiro. Thanks for the partners in the project, including Raiz and Navigator, and our team in Aveiro.
Hello, my name is Catarina Rebelo, and I will present to you the work entitled Fiber Recovery from Wastewater Treatment Sludge. This presentation will be divided in 4 parts: introduction, experimental, results and discussion, and conclusions. We all know the world faces the challenge of balancing the growing demand and competition for limited natural resources, where the solution for its sustainability is to adopt a circular economy. The pulp and paper industry have made a continuous effort to reduce its environmental impact. Through several projects, it has been studying ways to maximize resources and reduce process waste by making the best possible use of a product or creating a new raw material for other companies. In an integrated pulp and paper mill, primary sludge consists mainly of fibrous material but still contains a high inorganic part resulting from the paper process. So the problem was to be able to supply fibers from primary treatment sludges within the specification of the usual raw material of the recycled paper industry. This high inorganic load is incompatible with some paper, liner, or or cardboard applications where the recovered fibers can be used with some advantages. Therefore, the main purpose of this project was to find a mill-scale solution to reduce the ash content of the primary sludge. Moving on to the experimental part, so the first step to achieve this goal was to characterize the composition and dimensions of this material and conduct a solution research for technological hypotheses suitable for the separation of fibers from inorganic material. Based on characterizations made previously, available flows and lab test information, Andritz proposed the rotowash equipment. The last step was the recovering fiber trials at the navigator company Figueira Mill with rotowash pilot in order to obtain enough fibers to conduct an incorporation trial at Papeleira cardboard mill. The technological solution presented to us was the rotowash by Andritz. This equipment is used for de-ashing pulp and recovering fiber from filtrates and sludges. It can also be utilized as police filter for protecting shower nozzles and the like. The machine design is based upon well-proven pressure screen technology. Its main advantages are high yield and stock quality, thanks to selective fractionation and organic and inorganic material, is efficient in fiber recovery, low solids content in influent water, as a closed system and maintenance-free operation. Best adaptability to specific process conditions by simple modification of operation parameters. The purpose of fiber recovery trials was to test and validate conditions to obtain an efficient separation and a recovered fiber with less than 20% of ash in its composition. During the 3 days of testing, 2 conditions were tested: before and after the sludge thickener, where you can see in the location A and B in this wastewater treatment plant layout, but also different operation conditions such as the feed flow and reject rate in order to optimize the operation and obtain a stable setting. All these streams were sampled and analyzed in order to determine consistency and ash content. As soon as stable and optimized operating conditions were obtained, additional samples were collected for characterization. In addition to the consistencies and ash content in the different streams, the team also analyzed the ash and dryness content and properties of the recovered fiber obtained in the sludge belt presses. The second trial was the recovered fibers incorporation trial at Papeleira cardboard mill. This trial was to evaluate the impact of navigators' recovered fibers in their process and in the quality of their final product. In this one-day trial, several parameters were monitored. In the operation, we look at the production, paper machine velocity, specific steam consumption. In the pulp, we analyzed the paper machine headbox consistency, files retention, shopper regular test, pH, and conductivity. In the paper machine white waters, we looked at the pH and conductivity as well, total suspended solids, ash and dissolved calcium content, and in the final product were analyzed the normal paper making properties that usually Papeleira cardboard perform in their products. The recovered fibers were gradually added to the usual raw material of the Papeleira cardboard in the conveyor belt that feeds the pulpers, as you can see in the first photo. The controlled addition throughout the trial allowed to be tested an incorporation from 8 to 49%. As you can see in the second photograph, the paper machine producing paper with recovered fibers, and in the last one, the paper reel of final product. Moving on to the results and discussion of this work at these 2 trials. During the trial at Figueira Mill, many operational conditions were tested until it was reached the optimal reject and feed rate to produce a primary sludge with suitable percentage of ash. The best trials occurred with sludge after thickener and sludge before thickener with pressure stabilization to screen input using the pilot plant pump. According to the purpose of this trial, it was the operational conditions of trial 10, 11, and 12 that showed a more efficient separation. Rotowash streams function in this way. Feed is obviously the stream that contains the inorganic content that we want to separate from the fiber with the fiber. In this trial means the primary sludge stream. The accept stream, it's the ash enriched stream, and the reject one, it's the fiber enriched stream. The lower the reject rate flow, the greater the separation efficiency, which means fibers that we can obtain fibers that are freer of inorganic fillers. However, a greater loss of fiber may occur. In trial 12 was possible to obtain a fiber recovery of 62%, an ash removal efficiency of 61%, and a reject stream with 24% of inorganic content. After belt press, this material exhibited 20% of ash, our target, the maximum target for the product. As you can see, the normal ash content in Papelera cardboard fibers varies between 13 and 19%. Next was the recovered fiber incorporation trial. Was incorporated gradually fibers recovered from Navigator Rotowash sludge trials. We begin to incorporate from 8% to 49%. Beginning with the paper machine operation parameters, there was no relevant impact in the paper machine velocity or specific steam consumption, as you can see. In the pulp suspension analysis, refining degree Chopin-Euler test was increasing slightly with increasing incorporation of secondary fibers, however, without significant changes in water drainage. The paper machine white waters were analyzed as well. Up to 33% of incorporation, it showed an increase of 17% of ash content and a 6% of dissolved calcium in these waters. Up to 49% of incorporation, the maximum of this trial, we obtained an increase of 9% of dissolved calcium in the paper machine white waters. There was a decrease in fines retention and consequently an increase in suspended solids content in the white waters of the paper machine. There was no significant alteration in pH and water conductivity. Moving on to the fiber properties, as you can see, the dimensions of the recovered fibers, fiber length and width, are slightly below typical Papelera cardboard raw material fibers, simply because Navigator's process uses short fibers, as you know. In the paper-making properties, in general, these properties remained within normal Papelera cardboard ranges. As would be expected, there was a slight decrease of internal bond strength as the recovered fibers were incorporated. And finally, the conclusions of this work. Recovered fiber trials were successful, and the best results were achieved feeding sludge before thickener. For the level of incorporation of recovered fibers that the navigator company may provide to Papeleira cardboard, up to 8%, paper properties remain within normal Papeleira cardboard ranges, and there was no relevant impact on paper machine velocity or specific steam consumption, pH, and water conductivity. On the other hand, it was also possible to verify at this percentage of incorporation that potential impacts on their process, like an increase of dissolved calcium, ash content, and total suspended solids in white water circuits, were kept under manageable levels. And that's all. We've reached the end of this presentation. Thank you very much for your attention.
Eu não consigo ouvir.
Eu também não.
That's the point. That's the point. In mute. Thank you all for the presentation. We have some questions. Sorry. Está tudo fechado. Are you listening?
Sim.
Okay. We have some questions related with your presentations. Maybe I should start with this last one, fiber recovery. It's still fresh. I would like to know if you have seen any possible uses for the inorganic part of the solid content in the effluent.
No one wants. Yes, so far, we didn't study yet some uses for this current that it's difficult to incorporate in products, or until now, no. We didn't study anything.
Still related with this presentation. Have you seen any impact on the solid content in the final effluent? When you compare the solids in the final effluent, were they affected by the recovery of these fibers?
We didn't analyze the final effluent of Papeleira cardboard because they don't have their stream of final effluent is treated with another. I think it's the municipal wastewater treatment. So they treat their final effluent. So it's different from our mills, our navigator mills or other mills that have independent and a wastewater treatment from our process and our final effluent, and it's we have to monitor that parameters. But in this case, we only have made this trial in Papeleira cardboard, so because they don't need to have wastewater treatment, they don't analyze their final effluent, so we don't have that data.
Okay. Thank you. Let us go to Ricardo. We have a question from the audience. It's related with the energy consumption. Have you compared the energy consumption between integrated versus non-integrated mill? And in what concerns steam and electrical consumption?
Sorry, I didn't hear the last part of the question.
Regarding the energy consumption of integrated versus non-integrated tissue mill, how was steam and electrical consumption evaluated in what concerns the origin, fossil versus biomass?
Right.
And
yes,
also,
we compare.
And also, sorry, also considering the impact in the drying process. Right.
We compared the integrated with non-integrated system. This includes, in terms of energy consumption, the electrical consumption from the grid. In the case of the non-integrated, and in the case of the integrated, it includes the use of bioenergy from the pulp mill, which is transferred from the pulp mill to the tissue mill. And this is to substitute the use of natural gas in the gas boilers of the tissue mill. I don't know if I fully answered the question. So there was a question about the dryers. It doesn't, the difference between the non-integrated and the integrated does not include any substitution of natural gas in the dryers. So it's only for the gas boiler.
Well, I guess the point of the question was related with, so you replace pulp drive in the pulp machine by pulp drive in the tissue machine. I guess this is also an increase in the efficiency of the integrated mill.
So the definition, the integrated mill, it transport of pulp is via pipeline, so it's not via road transport. And also the integrated system, instead of using natural gas, imported natural gas, usually we substitute it with steam that comes from the pulp mill to the tissue mill. This steam is transported. Yeah.
Okay. Well, we're still related with this last question. Someone is asking about if you have considered the reduction of steam in the pulp mill.
Yes, there was a reduction of steam and electrical consumption in the pulp mill when we integrate, because we don't use so much steam and electricity to dry to produce market pulp. So instead, we have only slush pulp.
Okay. I guess Marinélia is back on the conference.
Yes.
Thank you for your presentation. We have some questions here. One of them is, have you seen any influence in the dust emissions in the boiler when using different types of biomass?
At this point, the only experience we have done was in an oven, not in the boiler. Okay, these results were produced in an oven in the laboratory scale.
Okay,
but in the future we are going to try to relate the biomass blends with the produced ashes, fly ashes in the boiler.
yes, because most of the boilers in pulp mills, they were prepared to use mainly eucalyptus bark or tree tops. But the more or less, what I'm asking is, do you see any ways, any clues to adjust the boiler operation depending on the type of biomass that is being used?
Okay. At this point, we are not trying to make changes in the operation conditions. We are just trying to study the biomass fluxes and their influence on the produced ashes, such as one of our results, we see that the acacia species are prone to produce ashes with high chlorine contents, for instance. So we are trying to find strategies like, okay, in the days where we have a lot of acacias in the fuel blends, the ashes produced should be put apart on that day, and they eventually be prone to have a pre-treatment before they are mixed with the ashes produced in the other days. And that's the kind of strategies that we are working with at the moment.
Okay, so I guess this is more or less related with another question that we have, which is considering the lack of biomass and that it is not possible to choose what biomass we use. What is the best strategy to increase the possibility to further valorization of the ashes?
Yes, it's to study the influence of each biomass using in the biomass blends and its individual influence on the ashes producers. Okay, I give the example of the chlorine content, for instance, but there are other factors like the sulfur content, for instance. We need to try to relate the influence of each biomass used in the blend with the produced ashes by itself alone, and then we on the days that those biomass species are present in higher amounts, we have to try to separate them because they are prone to be used in different valorization strategies. For instance, with high chlorines, for instance, those ashes should not be used in concrete applications because the chlorines are corrosive to steel structures. But maybe if they can be washed and then mixed with the ashes produced in other days, that problem can be resolved. I don't know if I answered the question.
Yeah, probably there might be some materials, some compounds that are used in the boiler construction that might not be compatible with some types of biomass. Is there any conclusions related with the possible impact in superheater corrosion in the boilers?
No, that is not in the scope of this study.
Okay. Let us finalize the sessions. I would like to thank you all for your excellent presentations and hope to see you soon. Thank you all. Bye.
Bye.